Today we are going to be talking about cascaded op-amp circuits. And all that means is what happens when we chain multiple op-amps together. Okay. This is going to be a fairly short lecture because for the most part, this topic is fairly straightforward. So let's consider a circuit where we have an op-amp here. And let's say, I'm going to call this amplifier A1 so that the voltage here will be the non-inverting input voltage of amplifier 1. So the subscript is for the amplifier and the superscript is telling us which pin we're at. This is my inverting input terminal. So this is going to be V1 minus. Here's my output pin. I'm going to put this label up here. The out one. And let's see, let's make this first amplifier a simple non-inverting amplifier. So I'm going to call this R2. Let's call this R1. Let's put our input voltage here. And then I'm going to have a second amplifier, and let's make this a inverting amplifier. So this is going to be amplifier A2. This is going to be V2 minus, V2 plus, V out 2. I'm going to have a feedback resistor here, which we'll call R4. And I'm going to put a resistor here, which is tying the output of amplifier 1 to the input of amplifier 2. This is going to be R3. And I'm going to ground this non-inverting input pin. Okay. So if I wanted to figure out how this system is going to behave, effectively what I would do is I would apply my process that we've been doing to this amplifier configuration, except that now I'm going to have to apply it to both amplifiers. The voltage present at the non-inverting input terminal of stage 1 is Vn. So the voltage present at the inverting input terminal of stage 1 is also Vn. And now when I apply Kirchhoff's current law at the at the inverting input node, this color, I'm going to do KCL here with the understanding that this current must be 0 amps. What I'm going to get is V1 minus over R1, excuse me, plus V1 minus V out 1 over R2 is equal to 0. So I have this relationship here. Let's call it 1. If I do the same thing to the second amplifier, I can see that V2 plus by inspection here is 0 volts. Actually, sorry, let me go one further step here. I'm simply going to substitute in that V1 minus is Vn. So I'm going to have Vn divided by R1 plus Vn minus V out 1 divided by R2 is equal to 0. I'm going to call this equation 1. Sorry about that. And then let's see, we're going to have V2 minus would be equal to V2 plus would be equal to 0 volts. Applying Kirchhoff's current law at the inverting input node for this amplifier, I'm going to be adding this current and this current together, with this current being 0 amps. And so that's going to look like V2 minus V out 1 divided by R3 plus V2 minus V out 2 divided by R4 is equal to 0. And substituting in that V2 minus is 0 volts, this is going to look like negative V out 1 over R3 minus V out 2 over R4 is equal to 0. And this is our second equation, and we now have a system of equations with two unknowns, assuming we know what our input voltage is, that we could solve. So what I'm going to do is I'm going to manipulate this algebraically here real quick. Okay. So for my first expression over here, I'm going to have Bn times 1 over R1 plus 1 over R2 will be equal to V out 1 divided by R2. Therefore, I could say that V out 1 is equal to Vn times R2 over R2, which is 1, plus R2 over R1, which is exactly what we should expect, because this first stage, if we ignore everything, the dashed line here, if we ignore everything to the right of this red dashed line and consider just everything to the left as a single stage, we can see by inspection, based on what we learned in our last class meeting, that this is a non-inverting amplifier. So of course it has the voltage gain relationship of a non-inverting amplifier, because that's literally how it's configured. Okay. If we do our mathematical manipulation on the second side here, so I'm going to have negative V out 1 divided by R3 will be equal to V out 2 divided by R4. We can rearrange this very slightly to find that V out 2 is simply negative V in, excuse me, negative V out 1 times a factor of R4 over R3. Again, this is nothing remotely groundbreaking. Everything to the right of our red dashed line, which is what I'm going to call stage 2 of this amplifier circuit, is a inverting amplifier based on how it's configured, where we're simply taking the output voltage of stage 1 as the input voltage of stage number 2. So putting these relationships together, what we would find is that V out 2, the overall output voltage of our system, is just going to be V in times 1 plus R2 over R1 times negative R4 over R3, where we can call this term AV1, the voltage gain for stage 1, and this term AV2, the voltage gain for stage 2, such that our overall closed loop voltage gain for our system is simply the product of the gain of the first stage times the gain of the second stage, because this is just the relationship of V out 2, the voltage applied at the, or taken at the output stage of op amp 2, divided by V in, the input applied at the input of stage 1. So this is all cascaded op amps is. If we don't recognize the type of amplifier that is used in each stage, we can still break things down stage by stage to figure out what that input-output relationship is for that particular stage, and then use the stages that we did recognize to just multiply those gains together. So as long as you can calculate the gain for any individual stage, then you can handle any type of cascaded op-amp circuit. So that's really all that I wanted to talk about for today. One thing that I do want to note here, because I get this question a lot, particularly with an example like this. If we put in numbers here, we would get a voltage gain that is just, excuse me, if we put in numbers for our resistors, we would get a voltage gain that is just going to be some negative number. And so the question would be, well, why would we want to use two gain stages like this if we're just getting a simple scaled version of our input signal? And the short answer is that for practical purposes, we actually wouldn't. Okay. It'll be rare that you'll cascade a non-inverting amplifier into an inverting amplifier or vice versa, because you can always just get the voltage gain just by using one of those stages. Where cascaded op amps really come into play is for more complex signal processing needs, right? So for instance, if you had two signals and you wanted to find the difference of those signals, you could use a differencing amplifier, and then you could cascade that differencing amplifier into a non-inverting amplifier or an inverting amplifier to scale up that difference, right? That would be an actual good application here, because you can't do that with a single amplifier stage. Another thing that's very commonly done would be running a weighted inverting summer into a second. So the output of that weighted inverting summer would be cascaded into the input of an inverting amplifier. And so that's simply going to add those signals together effectively, scale it by some amount, but put a negative sign. That's what the weighted inverting summer does. And then you can scale it by a different amount and make the polarity positive. So that's how load cells at weigh stations and stuff like that work in order to tell you how much weight is on the axle of a truck. They add all those together and then scale it using a specific resistor ratio to convert the output signal of those load cells into something that's measured in pounds or kilograms or tons, depending on what you need. So this example specifically was just to kind of show you the ropes of how cascaded op-amp circuits behave. And the short answer is they behave just like the individual stages chained together, because that's exactly what we are doing. Okay. The very last thing that I want to talk about here briefly, and this is really just to help you think about a homework problem. In one of your homework problems that I have assigned you, I have effectively given you a circuit similar to this, but I have tied together the two amplifier stages by applying feedback from the input of stage 1 to the output of stage 2. Because this isn't something that we can directly recognize, we would actually have to go and derive the relationship much like I did here. So we could do effectively exactly what we did here, except that our KVL equation, or excuse me, KCL equation at the inverting input node, this equation right here, would now contain an extra term because of the current that's flowing through resistor R5. And that's literally the only change that we would have to make to our circuit. And then we would be able to solve our simple system of 2 equations and 2 unknowns in order to get V out 2. All right, are there any questions? Okay, well, I hope you guys have a good weekend. Your exam, I guess, so Monday's class meeting will be for anybody that wants to pop on and ask questions. There is no lecture material or anything like that for Monday. It's just dedicated to answering questions about your exam. So see you Monday.